I want to tell you about something that puzzled me for years, and I'll bet it has puzzled you too. You've probably heard the famous story. You fire electrons at a screen with two slits, and somehow the electrons make a pattern like waves. Then you try to watch which slit each electron goes through, and the pattern changes. Now, most people think the mystery is just particles are also waves. And honestly, I used to talk that way too, because it's a convenient slogan. But then I realized something that changed everything for me. The double-slit experiment isn't just a cute paradox. It's the compressed essence of the whole quantum game. It's the place where your classical intuition doesn't just bend, it breaks. So let's take this one experiment, and I'll show you why I said it contains the only mystery of quantum mechanics. And I'll do it the only way I know how, by thinking it through with you, as if we're both standing at the apparatus together, quiet, curious, ticking, percussion underlay, like a mind starting to work. When I was teaching at Caltech, I had this constant problem. Students wanted pictures in their heads. They wanted to imagine a little electron as a tiny billiard ball, or as a little water wave, or as a cloud of stuff. And I understood the desire, because I have it too. I'm not immune. But quantum mechanics does not cooperate with the pictures we're used to. The trouble isn't that it's complicated. The trouble is that it's simple in a way that insults common sense. There's a chapter in my lectures where I start out bluntly. Things on a very small scale behave like nothing you have any direct experience about. They don't behave like waves. They don't behave like particles. And so we eventually give up and say, it is like neither. Then I say something even worse. Something that sounds like surrender, but isn't. I pick a phenomenon that is impossible, absolutely impossible, to explain in any classical way, and I tell you it has in it the heart of quantum mechanics. And I add the line people always remember. In reality, it contains the only mystery. Now, why did I talk that way? Because in the double-slit experiment, you don't just meet quantum mechanics as a set of rules. You meet it as a trap for the mind. Every classical explanation you try, every comforting story, walks you straight into a contradiction. And I know this because I've watched smart people do it. I've done it myself. You try one explanation. It went through slit 1, and the experiment punishes you. You try another. It went through slit 2. Punishment again. You try the compromise. It split and went through both. Punishment again. So let me set the stage the way I like, not with philosophy, but with a very concrete machine. Imagine I've got an electron gun. In front of it, a plate with 2 holes. Behind that, a screen. And I put a detector on the screen, something that clicks when an electron hits. Here's the first thing I want you to notice. This is a retention point because it seems trivial, but it isn't. What happens if I fire the electron so slowly that only one electron is in flight at a time? When you do that, you don't get half electrons. You get sharp clicks. 1 click, 1 electron. Always a lump. That's already telling you something. Whatever an electron is, it arrives as a discrete event. So far, fine. That sounds like particles. Now I open both slits and I count clicks at different positions on the screen. I build up a distribution. Where do the electrons land most often? And what do I get? I get an interference pattern. Peaks and valleys, like a wave. The probability distribution with both slits open is not the sum of the distributions from each slit separately. In my notation, it's not true that P1 tut P1 flup P2, and that right there is the crack where classical logic starts leaking out. Because if each electron goes through one slit or the other, you'd expect the probabilities to add, just like bullets. But they don't. Let me tell you where this gets interesting. It gets interesting exactly when you try to answer the simplest question a child would ask. Which slit did it go through? Hamus ICCU subtle tension swell. Curiosity turning into danger habs yul nates. Archival style animation of a simple apparatus electron gun. Gay 2 slits K detection screen. Then a growing interference histogram built from individual dots. My first instinct, everybody's first instinct, is to say, all right, an electron is a particle. It goes through slit 1 or slit 2. We just don't know which, so I make that a proposition. I call it proposition A. Each electron either goes through hole 1 or hole 2. Now, if that's true, the pattern on the screen with both slits open should be the sum of the patterns with each slit open alone. Because you would just have two groups, electrons that used slit 1 and electrons that used slit 2, and probabilities add like ordinary statistics. But the experiment doesn't do that. With both slits open, I get places on the screen where electrons almost never arrive, dark fringes, even though each slit by itself would send plenty of electrons there. That means opening the second slit can reduce the arrival rate at some places. If you believe in little bullets, that's a kind of insanity. So then you might try to rescue your intuition with a clever story. People love clever stories. They say maybe the electron goes through slit 1, then somehow loops around and gets influenced by slit 2 or bounces or does something complicated. But notice what that would imply. Closing slit 2 would have to change the distribution of electrons coming through slit 1 in a way that produces the precise interference curve. That's an awfully elaborate conspiracy, and it never works as a real mechanism, because the actual quantitative rule is too clean. Here is the clean rule: you don't add probabilities first, you add amplitudes. I say there are two complex numbers. Call them He1 and I2. They're probability amplitudes. The probabilities are high 1 die and 2 dies, but with both slits open, the probability is high 1 through 2 die. And that is exactly what waves do, not bullets. Now, you might think, fine, then the electron is a wave. So let's try that picture. If it's a wave, it goes through both slits, interferes with itself, and produces fringes. But then you look at the screen carefully at low intensity, and you see dots, single localized impacts, always dots. Not a smeared wave. A wave would deposit energy continuously. Electrons don't. So the electron is not a wave in the everyday sense, and it's not a particle in the everyday sense. That's where I started to see the pattern. Quantum mechanics is not telling you what the electron is. It is telling you what happens when you set up an experiment. I remember the moment I realized I had the story backwards. The experiment isn't revealing a hidden path. The experiment is creating the conditions under which path is or isn't even a sensible word. Ha messasis a gentle click motif. Since to imagine detector clicks I will not s show two curves labeled P1, P2, then the interference curve P12, which is visibly not P1, P2, overlay the amplitude rule 1 fun T2 dabive. Now we come to the part where people start saying mystical things. They say, observation changes reality, or the electron knows you're looking, or consciousness collapses the wave function. I never liked that style. Not because it's definitely wrong, because in quantum mechanics you must be careful what you call wrong, but because it encourages sloppy thinking. It makes you feel like you've explained something when you haven't. So I ask a more practical question. Can I design an apparatus that tells me which slit the electron goes through? Yes. I can watch it by scattering light off the electron near the slits. Put a strong light between the holes. Every time the electron goes through, it scatters a photon. I see a flash near slit 1 or slit 2. And this is crucial. I never see both at once. When I look, it really does appear to go through one hole or the other. So proposition A suddenly looks true again? But now comes the punchline. When I do this watching experiment, the interference pattern disappears. The distribution on the screen becomes the simple sum P1 P2. No fringes. Now, you might say, of course, your light hit the electron and disturbed it. That's just classical disturbance. All right, so I try to be gentler. I dim the light. But dimming the light doesn't make each scattering event smaller. It just makes scatterings rarer, because light comes in photons, lumps. So what happens is deliciously aggravating some electrons get by unseen. And those electrons still make an interference pattern, but the ones I actually see, the ones that scatter a photon, do not. So it's not the human mind doing anything. It's the physical interaction required to gain which path information. The world pays a price for knowledge. And then you get the next clever idea. This one is a favorite use light with a longer wavelength. So each photon has less momentum and gives the electron a smaller kick. Good, I do that. I make the wavelength longer and longer. And then I run into a new problem. When the wavelength gets longer than the slit separation, the picture I get becomes fuzzy. I can no longer tell which slit the electron went through. The apparatus itself cannot resolve it. And precisely in that regime, where the which path information is unavailable, the interference returns. Now you see what's happening. It's not that the electron is deciding to be a wave or a particle because it's being watched. It's that the conditions for interference are exactly the conditions where the alternative paths remain indistinguishable. But then something unexpected happened. The more gently I tried to look, the less the very question, which slit, even made sense. Here I bring in Heisenberg, not as a character in a drama, but as a man who had the nerve to accept what the experiments were screaming. He proposed the uncertainty principle, and in the language of this experiment it becomes, you cannot design an apparatus capable of determining which slit the electron goes through without disturbing the interference pattern. And I'll tell you something personal. This bothered me, not because it was mysterious, but because it was final. It wasn't ignorance we could fix with better instruments. It was a limit built into nature's bookkeeping. Her visual note est. Show photon scattering near slits, split screen, which path known. No interference, which path unknown. Bay interference returns a mu CCUE. Tension resolves into a calmer, explanatory tone. Now, I asked myself, if that's really the rule, if interference depends on indistinguishability, then what about everything else in quantum mechanics? Energy levels, tunneling atoms, chemistry, are they all just fancy variations of this same trick? And here's where my understanding completely shifted. This is where my understanding completely shifted. Quantum mechanics is not particles behaving like waves. It is amplitudes adding and probabilities coming from squaring. Look, if you accept just that, an enormous amount follows. Take the simplest quantum statement. The probability of an event is the absolute square of a complex number, the probability amplitude. That already kills classical determinism. You don't predict exact outcomes, you predict odds. Then comes the central rule: if an event can happen in several alternative ways, the amplitude is the sum of the amplitudes for each alternative. That's where interference comes from. And then the third rule is the one that ties the knot around your intuition. If the experiment is capable of determining which alternative occurred, then you sum probabilities, not amplitudes. The interference is lost. Now notice what I've just done. I've taken the double-slit experiment and turned it into a set of principles that apply to any quantum phenomenon. The two slits become two alternatives. The screen position becomes the event we measure. The which path detector becomes or any record in the world that could, even in principle, distinguish the alternatives. So I started to see the double slit as a kind of Rosetta Stone. Let me show you a thought experiment I used to imagine. Suppose the slits aren't holes in a plate, but two possible histories of a particle. For example, in an atom, an electron can go from one place to another in many possible ways, many possible quantum paths. Classically, you would pick the one path that obeys Newton's laws. But in quantum mechanics, you must consider all paths, each with an amplitude, and add them. That idea later became very natural to me when I developed the path integral method. Nature explores alternatives by adding amplitudes. And the double slit is the simplest case, two prominent alternatives, and the interference of their amplitudes. Now you might say, but quantum mechanics has much stranger things than two slits. It has entanglement and spins and Bell's inequalities and all that. Yes, but here's what changed everything for me, even those stranger. Things are still built on the same skeleton. Superposition is just the statement that alternatives carry amplitudes, and you can add them. Measurement is just the physical creation of a record that distinguishes alternatives, forcing you to add probabilities instead. Entanglement is what happens when the alternatives of one system are linked to distinguishable alternatives of another system, so that information exists in the joint state, and interference can vanish locally. I'm not asking you to swallow any interpretation. I'm telling you, the rules you need are already visible in the double slit. Now, here's what changed everything for me. I stopped asking, what is the electron really doing? And I started asking, what are the alternatives my experiment allows, and are they distinguishable? Javi Isuel nos blackboard animation. Alternatives. Go at amplitudes. Go square to get probability. Then distinguishable. Yes, geb add probabilities. No gay interference term appears. Amuse cue. A forward driving but restrained rhythm, like building toward a big idea. Let me build toward the real reason I said that outrageous line, that this one experiment contains the only mystery. In classical physics, if you don't know which slit the particle went through, that's just a gap in your information. The particle still went through one slit, and if you had better eyes, you could find out. Quantum mechanics is different in a more radical way, the absence of which path information is not merely ignorance. It is a physical condition that changes what can happen. The interference pattern is not a picture of a particle's path. It is a picture of the structure of possibilities. And possibilities are not metaphysical fantasies. They are encoded in amplitudes that add and cancel. When people say, the electron interferes with itself, that's not quite right. The electron is not a little object that splits and reunites like a water wave. What interferes are the probability amplitudes associated with alternative histories. And when you mark the path, when you make the alternatives distinguishable, you don't force the electron to choose. You destroy the conditions that allow the amplitudes to combine. You've changed the experiment's logical structure. This is where my intuition failed me the first time. I kept thinking the electron had to have a story, like a baseball has a story. But quantum mechanics doesn't give you a single story. It gives you a rule for computing what happens when stories are allowed to remain indistinguishable. And that's why the double slit feels like a prank. It attacks the deepest classical habit that events have definite histories independent of what can be known about them. Everything I thought I knew was about to change, because I finally understood that which slit is not a factual question unless the world contains a fact that answers it. Nis dissolve from two physical slits into a branching tree of alternative histories. then show some branches recombining S interference when unmarked and staying separate, no interference, when marky, musically CUE drop the rhythm, leave a quiet, spacious tone before the eureka, and then it hit me. The double-slit experiment is not important because it's weird. It's important because it forces you to accept the operating system of quantum mechanics in its purest form. Here's the eureka in my own words. In that experiment you can see, in one place, the three core rules: amplitudes, addition, and the loss of interference when alternatives become distinguishable. That's why I said it has in it the heart of quantum mechanics. In reality, it contains the only mystery, and we cannot make the mystery go away by explaining how it works. We will just tell you how it works, because the double slit is the simplest stage where the quantum rules are unavoidable. There's nowhere to hide. And once you accept those rules, quantum mechanics isn't a collection of separate miracles. It's one consistent framework. Atoms aren't magical. They're interference patterns in the space of possibilities. Chemistry isn't mysterious. It's interference patterns between electron alternatives. Even the stability of matter, why your hand doesn't fall through the table, comes from the same amplitude bookkeeping. Now, does that mean you understand quantum mechanics the way you understand gears in a watch? No, nobody has found machinery behind the law. That's another line I wrote because it's honest. No one has found any machinery behind the law. But you can understand the logic of it. You can become fluent in the rules. And you can stop demanding a picture that satisfies my everyday imagination. So when I say the double slit explains all of quantum mechanics, I don't mean it contains all the mathematics. I mean it contains the essential conflict between classical reasoning and quantum reality. And it shows you the way out. Stop asking for a single history and compute with amplitudes. Harvis ul notice show the three-rule summary as a clean blackboard moment. Highlight the phrase, only mystery. Now I'll tell you why I still love this, even after all these years. The double-slit experiment is a reminder that nature is not obligated to match our instincts. Our instincts were trained on rocks, spears, and sunsets, big things that average out. But in the small world, the universe keeps exact books. It adds amplitudes, not narratives. And there's a strange kind of humility in that. Physics, especially quantum mechanics, forces me to admit I can predict probabilities with absurd accuracy, but I don't get to demand a picture that satisfies my everyday imagination. Yet I don't find that depressing. I find it exhilarating, because it means reality is richer than the stories we grew up with. It means there are layers of logic underneath the obvious, and we're lucky enough to peek at them. If you take anything from me, take this. Don't be ashamed when quantum mechanics feels mysterious. It is mysterious in a very precise way. But the mystery is not a fog. It's a clean, sharp edge. Whether alternatives interfere depends on whether the world contains information that can distinguish them. I hope you can see what I see when I look at that two-slit apparatus. Not just a paradox, but a little window into how the universe computes. This is the beauty of physics, and I wanted you to experience it with me.